Greetings to all viewers. This is Professor Ankit Singh. We'll now start with the numericals on pavement design. Okay, we have the first numerical to find out the ESWL, okay, or equivalent single wheel load. We'll have a look at this numerical. The question is as follows. Calculate ESWL of a dual wheel assembly carrying 2044 kg each for trial pavement thickness values of 150, 200 and 250 mm. Center to center spacing between two tires is 270 mm and clear gap between the walls of the tires is 110 mm. Okay. So this is the question. We need to find out what would be the ESWL values at the depths of 150, 200 and 250 mm. Okay. So in the solution part, let us look at the first what is given. Okay. So we have the total load on in single wheel. Okay. So capital P is given 2044 kg. D is given 110 mm. Okay. D is nothing but the clear gap between the two wheels. Then center to center spacing between two tires is S and it is given as 270 mm. Okay. So as we have already learned in the concept of ESWL how we need to find out the value of ESWL for varying depths. Okay. So we need to plot a graph, and to plot the graph we need the values of P, D by 2, 2P and 2S. Okay. So we have P, we can find out 2P, 2 into 2044 is nothing but 4088. Then we have S, so 2S would be 270 into 2, that would be 540, and D by 2 would be 110 divided by 2, it is 55. Okay, now what we need to do is we need to plot a graph. This is a log graph. Okay, if you do not have a log graph sheet with you, then you can convert the values, take the logarithm of each of the values and plot it on a normal graph sheet. Okay, so we have a graph sheet here. We have a log graph sheet. Okay, along the x-axis we need to take thickness, along the y-axis we need ESWL. Okay, so the first point would be P comma D by 2. We have the P value as 2044 and D by 2 as 55. So citing D by 2 here and P here, we have a point here. Okay, X. Then for point Y we need 2P and 2S. Okay, so 2S is 540, 542 would be here somewhere. Okay, and then 2P is 4088, it is somewhere here. So the point we got Y. Okay, so we have X and we have Y. Now what we need to do, we need to join these 2 points using a straight line. So we have joined X and Y. Now what do we need? We need the ESWL values at 150, 200 and 250. So what we need to do is we need to locate where 150 is here, extend a vertical to cut the graph at this point, then extend a horizontal to cut the y-axis. So this is nothing but the ESWL at 150. Similarly, you need to do it for 200. So you extend a vertical from this point, it will cut here, then you need to extend a horizontal and you get the ESWL value here. Similarly, you do it for 250 mm. Okay, and then you need to tabulate these values. Okay, so for pavement thickness of 150, ESWL that you got is 2760. For 200 it is 3000 and for 250 it is 3230 kg. Okay, this here is the end of this numerical. Okay, so now we have the next numerical. The question is as follows. Using the data given below, calculate the wheel load stresses at interior, edge and corner regions of a cement concrete pavement using Westergaard's stress equations. Also determine the probable location where the crack is likely to develop due to corner loading. Okay. So what is given to us? Wheel load P is given as 5100 kg. Modulus of elasticity of cement concrete E is given as 3 into 10⁵ kg per centimeter square. Pavement thickness H is given as 18 centimeters. Poisson's ratio of concrete is given as mu is given as 0.15. Modulus of subgrade reaction capital K 6 kg per centimeter cube, and radius of contact area small a is given as 15 centimeters. This is what is given to us. Okay, so going ahead with the solution, we know radius of relative stiffness is given by this formula, where L is equal to EH cube divided by 12k into 1 minus mu square whole raised to 1 by 4. Substituting the values of E as 3 into 10⁵, H is 18, K is 6 and mu is 0.15. Solving this, we get the answer 70.6 centimeters. Okay, so we have L here as 70.6 centimeter. Now we need to find the equivalent resisting section, the radius of resisting section. Okay, so for that, firstly what we do is we find out whether A by H is less than or greater than 1.74. okay, so A by H is A is 15, H is 18. What we got is 0.833. Now this is greater than 1.74. Hence we need to use the formula of B. B is equal to root of 1.6a square plus h square minus 0.675 h. Substitute the values of A as 15 and H as 18, and then solving you get 14 centimeters. So now you have the value of small l and small b, and Westergaard's equation for interior stress is given as 0.316 p by h square 4 log 10 l by b plus 1.069. Substitute the values of p, h, l and b in this equation, and then solving you get 19.3 kg per centimeter square. Similarly, equation for stress at the edge is given SE is equal to 0.572 P divided by h square into 4 log 10 L by B plus 0.359. Substituting the values of P, H, L and B and solving, you get 28.54 kg per centimeter square. Then you have the equation for stress at corner, which is given as 3P by h square into 1 minus a root 2 divided by L whole raised to 0.6. Substituting the values of P, H and A and L. Okay, solving you get 24.27 kg per centimeter square. Okay, so here you can note that the stress is maximum at the edge, which is 28.54. okay, then we are also required to find out the location where corner load crack develops. Okay, so the formula is given here. Location where the crack is likely to develop due to corner loading, the distance from the corner of the slab. Okay, from the corner of the slab at a distance of x, which is equal to 2.58 root of AL. Okay, so we have the value of A and we have the value of L. Substituting that, we have the answer 84 centimeters. Okay, this is for the solution in this problem. We'll move to the next problem now. The question is as follows. Determine the warping stress at interior edge and corner of a 25 centimeter thick cement concrete pavement with transverse joints at 5 meter interval and longitudinal joint at 3.6 meter interval. The modulus of subgrade reaction K is 6.9 kg per centimeter cube. and the radius of loaded area is 15 centimeters. Assume maximum temperature differential during day to be 0.6 degrees per centimeter slab thickness for warping stress at interior and edge, and the maximum temperature differential of 0.4 degrees per centimeter slab thickness during the night for warping stress at corner. Okay, so there are different values for interior edge and different for corner. Okay, additional data which is given is E equal to small e equal to 10 into 10 raised to minus 6 per degrees centigrade, and capital E equal to 3 into 10 raised to 5 kg per centimeter square. Mu is equal to 0.15. Okay, so in this solution, firstly we have the given entities h, that is thickness 25 centimeters, capital E 3 into 10 raised to 5, mu 0.15, a radius of contact area 15 centimeters. Then we have temperature coefficient 10 into 10 raised to minus 6 per degree centigrade, Lx and Ly. Okay, now these here are important. This is the length of the slab and the width of the slab. Okay, or you can also say that it is the spacing between the transverse joints and the longitudinal joints, etc. Okay, so temperature differential is 0.6 degree per centimeter for slab thickness during day and 0.4 degrees during the night. So temperature differential during the day T1. Okay, during the day it is given 0.6 into 25. Okay, since it was for per centimeter slab thickness. Okay, so our total slab thickness is 25. So if for 1 centimeter it is this much, it is 0.6 and 0.4, then for 25 centimeter it would be how much? We need to multiply. Okay, so T1 is 0.6 into 25 equal to 15 degrees, and T2 is 0.4 into 25, it is 10 degrees centigrade. Okay, now again we need to find out radius of relative stiffness, that is L. We have the formula here, EH cube divided by 12k into 1 minus mu square whole raised to 1 by 4. Substituting the values of E, H, K and mu. Okay, if we substitute them here and solving, we get 87.2 centimeters. Okay, now we need to find out the values of Lx by L and Ly by L. Okay, now why do we need these? I'll tell you later on. Firstly, let us find out the values of Lx by L. Lx is 500. Okay, L we just found out is 87.2, so 5.73 is Lx by L. Then we need to find out Ly by L. Okay, Ly by L is 360 by 87.2, it is 4.13. Okay, now we need these Lx by L and Ly by L values to find out Cx and Cy. Okay, so this standard curve would be given to us in the question. Now we have the values of Lx by L and Ly by L along the x-axis and value of Cx and Cy along y-axis. So we need to find out Cx and Cy. We have Lx by L is equal to what? 5.73. So from the x-axis 5.73 would be somewhere here, extend it, it would cut somewhere here and extend it to the horizontal, you would get some value between 0.8 and 0.9. Okay, we get it as 0.88. that is how you obtain Cx. Now do the same for Ly by L, so 4.13 somewhere around here, extend the vertical from here, then extend horizontal, you get it something in between 0.6 and 0.5. okay, you get it as 0.54. okay, so you have the values of Cx and Cy now. So We have the equations for warping stress. Warping stress at interior region of the slab during day is given by STI equal to capital E into small into t divided by 2 into Cx plus mu Cy divided by 1 minus mu square. Substituting the values of capital E, small e, t, Cx, mu, Cy and mu. Okay, we have all these values. Just substituting the values and solving, we get the answer 22.15 kg per centimeter square. Okay, so now the next thing is we need to find out warping stress at edge during the day and substituting the relevant values capital E, small e, t, mu and higher of the two values. Okay, for STE we have two formulae in which in one formula we use Cx and one formula we use Cy. Okay, and we need to adopt whichever is the higher value. Since Cx is greater than Cy, therefore we adopt Cx. So Cx into capital E into small e into t divided by 2. Substituting the values and solving, we get 19.8 kg per centimeter square. Now third one, warping stress at corner region during night. Substitute the values in this equation. STC is equal to E capital E into small e into t divided by 3 into 1 minus mu into root of a by L. Substituting these values here and solving, we get 4.88 kg per centimeter square. Okay, so this is the solution for this problem. The next numerical is as follows. I'll read out the question. The spacing between the contraction joints of a cement concrete pavement is 4.2 meters. Determine the tensile stress developed in the CC pavement due to contraction if the coefficient of friction between the bottom of the pavement and supporting layer is 1.1 and the unit weight of CC is given 2400 kg per meter cube. Okay, here CC stands for cement concrete. So given is capital L, okay, that is the spacing between the contraction joints is 4.2 meters. Coefficient of friction F is 1.1 and specific density of concrete is given as 2400 kg per meter cube. We have the formula for frictional stress where SF is equal to WL into F divided by 2 into 10 raised to 4. Substituting the values of W, L and F and solving, we get the answer 0.554 kg per centimeter square. Okay, so this completes the solution. Thank you.